Thanks, Michael. I figured a good talk to start off the topology seminar is what is a topological space. And I thought I'd present sort of a different perspective on it than what you'll find in most textbooks. So here's what a topological space is, right? You have a set here, and you have a collection of distinguished subsets, and you call it a topology. If it contains the empty set universe, it's closed under finite intersection, and it's closed under arbitrary universe. Classic. I want to present this different idea that when you have a topological space, right, this tau, it's not just any arbitrary collection of sets. It's actually generated by the balls of some generalized metric. And so we can start off with how does this work in metric spaces. So it's how you generate the topology from metric space. You look at all the balls with size epsilon greater than 0 at every point in your space, and these balls, right, that are a set of points that are distance less than epsilon from that point x. And the reason we like these spaces is because you can actually use the metric d rather than just looking at the open sets themselves. So you can think about it in terms of distance, not just about in terms of open sets. Right? So here, classic example, right? The function is continuous if and only if, right, for every sequence xn whose distance to x goes to 0, the distance in the codomain, so f of xn and fn, have distance going to 0. That's just not the only reason we like it. It's because you can also define objects which are not entirely seen by the open sets themselves. Right? So in metric spaces, you have, for example, a Cauchy sequence. Right? And Cauchy sequence, right, is the distance between xn and xn going to 0. And this object is not topological. This notion is not seen by the open sets themselves. And the reason you can tell this is that there's two metrics on the space which generate the same topology, but they generate different Cauchy sequences. Right? Good, I fixed that. And then you have another example of something, the Lipschitz continuity, which is right, you have the distance between f of x and f of y being less than or equal to some constant, the distance between x and y. Again, this isn't noticed by the open sets. And so even for purely topological problems, stuff that depends only on the open sets, when you have a metric space, you can use these non-topological notions of Cauchiness and Lipschitz continuity and other notions inside of your proof, which allows you to have much more proof techniques and define many more objects. So even though these notions of Cauchiness and Lipschitz are not entirely dependent on the topology and depends what metric you pick, it turns out not to matter when proving results, right? which is a really nice thing. Okay. So obviously if we want the sort of idea of a metric that works for every single topological space, we're going to have to lose some nice properties of metric. So we can start off. Here's your axioms of metric. Distance between x and x is equal to 0. You have triangle inequality. You have the symmetry. And then you have if 2 points have the same distance 0, then they are the same point. Okay. So one of the first things to consider is that some topological spaces, they aren't Hausdorff. And all metric spaces, they are Hausdorff. And where that comes from is in this axiom 4, right? 2 points, if they have the distance 0 to each other, then they are the same point. Right? And you can consider something trivial like the indiscrete topology, where the only open sets are the empty set and the entire space. So any 2 points here, right, they're not distinguishable by the open set, so they shouldn't be distinguishable by any sort of balls which you define. So in some sense in the space, the 2 points, they have distance 0 to each other. And the general idea here is a pseudometric. So what we've done to go from a metric to a pseudometric is we've deleted that axiom 4. So we have everything else, we have the symmetry, we have the distance to itself is equal to 0, and we have triangle inequality. And these pseudometrics, they induce a topology the exact same way you do for a metric. You just replace the balls, except this is no longer a metric, this is now a pseudometric. And everything else goes through. Yeah. So for your indiscrete space, it is indeed generated by a pseudometric. The distance between any 2 points is equal to 0. So you can check that that map is indeed a pseudometric. Yes, the distance between x and x is 0. It satisfies triangle, yeah. And 0 is less than or equal to 0 plus 0, and it's definitely symmetric. Yeah. And then also it does generate the indiscrete space, because if you look at any one of your balls, right, for any x and any epsilon bigger than 0, the ball is just the entire space. A slightly more interesting example of this is look at like the space of integral functions, and you can sort of define a notion of distance on it by the integral of the absolute difference between f and g. And you can check, this is a pseudometric, distance between f and f, that's equal to 0, it's definitely symmetric. And you get triangle inequality, the set of triangle inequality from the absolute value. Yeah. But because it's pseudometric, you end up with some sort of strange property. So we're going to have a sequence fn, which is constant equal to f, which is just equal to 0. And then we're going to have a function g, which is equal to 0 everywhere, except for the origin when it's equal to 1. And what you have is that the distance between fn and f goes to 0. The distance between fn and g also goes to 0. So because we've lost this separation, we've lost that axiom for the metric, that sequence fn, it doesn't have a unique limit in this space. And in fact, it has uncountably many limits, just by the same trick, just move to the point where you want somewhere else. Okay. So a lot of spaces are pseudometrizable. You have any second countable, so there is this countable base for your space, and T3 means you can separate a point and a closed set by these open sets. Any space like that is pseudometrizable. And this is slightly different from a famous result response metrization model theorem. This says that any second countable regular space is metrizable. So regular just being T3 and also Hausdorff. Here's some other nice properties. So you have a pseudometrizable space, which just means your open sets are generated by these balls of these pseudometrics. It is metrizable if and only if it's Hausdorff. So we're moving the axiom forward, we've just gained sort of these Hausdorff, these non-Hausdorff spaces. We've left everything else. Cool. And now that we have these sort of this metric, we can again use it to define sort of notions, define topological notions. We have continuity has the same exact formula you have for metric spaces now inside of pseudometric. So if xn goes to x, then f of xn goes to f of x. And you can write that in terms of the metric. And then you can also define these non-topological notions. Cauchy, same exact definition as always. But here we're not done, right? There are topological spaces that are not pseudometrizable. Just by deleting Hausdorff, deleting that axiom 4, we have not gained all topological spaces. So we can just go through the next axioms. We've got axiom 3 here, which is some sort of symmetry. And not all spaces satisfy this. You have the Sierpinski space, where the open sets, it's the empty set, the set containing 0, and then your entire space. So what you have here is that every neighborhood of 1 is also a neighborhood of 0. But there is a neighborhood of 0 that is not a neighborhood of 1, which is really weird. So you have weird properties like every sequence which converges to 1 also converges to 0. But then you can have a sequence which converges to 0 but doesn't converge to 1. And the example, right, just take the constant sequence equal to 0. So you have this weird like lack of symmetry in your space.
Wait, sorry, can I ask a quick question
Yeah.
about T3? So
Yeah.
I thought T3 implies T, like Hausdorff.
Yeah, it depends on who you ask, depends on the definition. Yeah. Sometimes you have the nice ordering T5 implies T4 implies T3 implies T2.
Okay.
And some definitions, T4 doesn't imply anything else, T3 doesn't imply anything else, and T2 implies T1 implies T1. It just depends on how you want to define
So
it.
what do you mean by T3?
T3, you can separate a point and a closed set. By
You want
these.
maybe to draw a picture.
Want to draw the picture?
There's a marker.
So the problem is that a singleton isn't necessarily.
Isn't necessarily closed. Yes. Right. Other questions? No? Good. So for this sort of space, what you have in some sense is that the distance between 1 and 0 is equal to 0. The distance between 0 and 1 is bigger than 0, because it's sort of like the idea 1 cannot be distinguished from 0, but 0 can be distinguished from 1. Weird sort of stuff comes out. And here's a lovely picture I stole from that paper. Apparently these sort of ideas appear a lot in your like optimal control type thing. So you consider like how much effort does it take to go from X to Y. It's very different for how much effort it takes to go from Y to X. When you're going uphill is harder, going downhill is easy. So you have this lack of symmetry in that. Okay. So if you just delete an axiom 3, delete your symmetry, you end up with a a quasi-pseudo-metric. All right, you can also guess how you get just a quasi-metric. And then for these spaces, right, and you generate the topology in exactly the same way. You know, you take these open balls, right, and they form a basis for the topology. But something to be careful about, now that we've lost symmetry, it really matters what order x and y go in here, right? So the ball at x, I'm putting x in the first coordinate and putting y in the second. If you did it back to front, put y first, x second, you end up with a different topology. Right, it's also the reason I'm putting the distance between x and xn goes to 0. Because the ordering matters once you lose the symmetry property. Cool. So we have some nice properties of these quasi-pseudo space. Any second countable space is quasi-pseudo-metrizable. Right. We had regular, we had metric. When we had T3, we had pseudo-metric. Delete all the separation axioms that only have second countable. Now you're quasi-pseudo-metrizable. It's quasi-pseudo-metric that generates your space. Right. And then you have, right, all these nice properties. You can use the metric to define these topological notions, right? Continuity, it's the same formula I've written on the past 3 examples of this, except now this ordering actually matters. F of x goes in the first coordinate, f of xn goes in the second. Right. So something like cosinus, it's the exact same definition as before, and we don't actually care about the ordering. You can define this notion of like a left cosy and right cosy where you can start to take into this ordering, but I won't worry about that. Okay, so we've returned back to Sierpinski space. And sort of like exactly what we said before worked. You just define the distance between 0 and 0 to be the same as the spin 1 and 1, to be the same as the spin 1 and 0, and you call that 0. And you define the distance between 0 and 1 to be 1. So you can check your axioms. It's not so nice, right? Distance between like x and x is always equal to 0. And then triangle inequality, you can sort of do it in cases. I know of like clean proof for it. Okay. And here's sort of my favorite example of a quasi-pseudometric. This is one, it's on the reals, and you define the distance between x and y to be x minus y, when x is bigger than y, and it's 0 if x is less than or equal to y. And so very much not symmetric. Right. And then again, you can check your axioms like triangle inequality holds here, it's not exciting, and q of xx is definitely equal to 0. And they look at what the open balls look like. So if you consider any y that is bigger than x, the distance, whoops, that should be a q. The distance is just equal to 0. And so this is trivially satisfied for every y bigger than x. And the only part the epsilon actually matters is when y is like this epsilon distance to the left. So then you can look at what like the topology of these balls induce, and this is right order topology, where you have all your infinite rays going off to the right. That's annoying.
You can move it.
Yeah, but
You can click on more and then hide.
more and then that's
Almost.
it's quick. Okay, can we just shove it all the way off to the right? Okay. Okay, no one asked me to do anything. Oh no! No, go away. Please. How did that go? We're fine. Alright, cool.
You turn off your audio as well.
No, the audio was always off. The audio's on this one.
Ah, I see. Yeah.
Cool. So this is the reason I really care about this, is that you have a function that goes from reals with the Euclidean metric, and going into the reals with this quality metric, right, x minus y, right, and then 0. And if it's continuous with these respective topologies, it's called lower semi-continuous, right? Which is slightly different to the normal definition of lower semi-continuity, but it's one I quite like. And you can sort of like really see like there's asymmetry in Q when you consider functions sort of like this. So this function very much not continuous into Euclidean space, but I claim it's lower semi-continuous. So it's continuous when the codomain has this Q metric, And so the only interesting part is at 0. Okay, yeah. So you can take any xn that goes to 0, and then as xn goes to 0, f of xn must be greater than or equal to f of 0. So you look at the distance between f of 0 and f of xn, because f of xn is bigger than f of 0, the distance is just equal to 0. Right? So trivially, that distance, that tends to 0. If you then flipped it and considered something that sort of looks like this, now this won't be lower semi-continuous, and you can sort of just do the same proof. Right? If xn goes to x, now you have g of xn is less than or equal to g of 0. So this q distance between g of 0 and g of xn is just the difference between them, and so it just reduces down to Euclidean. And because it is not continuous with Euclidean in the codomain, it's also not lower semi-continuous. Okay. So this idea of going down is somehow privileged than going up when you have this quasi-pseudometric in the codomain. Okay, but we still aren't done. There are still spaces which aren't quasi-pseudometrizable, aren't generated by this quasi-pseudometric. Okay, so we look at the axioms we have left. It's like what's really left to delete. You can
We don't have an example here
But the example is?
of a topological space that's not quasi-pseudometrizable.
Yeah.
Oh, you have it, yes.
Yeah. Next few slides, you'll see it. Yeah. All right. So if you just delete the distance between x and x is equal to 0, then you don't really end up with something that's like agrees with any generated topology. Because you take the sequence just xn equals to x, right? A constant sequence. Then you definitely require in any topological space for xn to converge to x. Right? But then you look at the distance between x and xn, and now that doesn't go to 0. So sometimes you want to define the convergence through the metric, it can't agree with any convergence generated by a topology. So we don't want, that one has to stay. And then you can delete triangle inequality if you want, but at that point, what are we left with? We're left with a function with product space that's 0, along diagonal. So that's all it's doing. Okay. And that's something I really want to call like a generalized metric. Okay, but let's go to this example that is not quasi-pseudometrizable. And the way you show these is it's just, for any x, look at these balls of radius 1 on n. Right? This forms a neighborhood base at x. You can shrink down along these 1 on n sequences, and that forms a full neighborhood base. So what you get from that is all the quasi-pseudometrizable spaces, they are first countable. So if you want an example that's not quasi-pseudometrizable, take a space that isn't first countable.
What is first count?
Countable neighborhood base. So there's this countable collection of sets like around x. That's with every neighborhood. Right? That's one of these contained in it. Okay. And the nice example is just R to the R. Take a large product of the reals. Right? It definitely works. And the idea behind it is you just look at what, say, like basic neighborhoods look like. Along finite many coordinates, they're like open sets in the reals, and along every other thing, it's just the entire real line. If you want to generate these countable collection which controls all these neighborhoods at once, it's not possible. Or you basic neighborhood control only finitely many, and then you want countably many of these to control uncountably many neighborhoods. It doesn't work. But R to the R, it's quite a nice space. R to the R, depending on who you ask, it can be considered the space of all functions from reals to reals, or it just is that space. And what the product topology on R to the R is, it's just the topology of pointwise convergence. By that, I mean that Fn goes to F, if and only if for every x in the domain, Fn of x goes to F of x, right? Pointwise convergence. But here, this convergence, this part here is very much like nice, sort of metrizable. So you can define this dx between f and g to just be the Euclidean distance between f of x and g of x. Then what you end up with is that Fn converges to f, if and only for every x. This dx metric between Fn and x goes to 0. So while R to the R is not generated by any quasi-pseudometric, so any metric, it is generated by an uncountable collection of pseudometrics. So this is very much, a dx of f and f is definitely equal to 0. Triangle inequality definitely holds, definitely symmetric. But if the distance is equal to 0, you can only guarantee that f of x is equal to g of x. And they can be arbitrarily outside of that. So it's not a full metric. So you have this uncountable collection of pseudometrics. And we can sort of extract out this general principle. So if we have a set of quasi-pseudometrics Q, then you can induce a topology from it by taking your regular open balls, so open balls at epsilon, of radius epsilon at point x, using metric Q inside of squid Q. I think I wrote that. Yeah. And you can take these as forming a subbase for a topological space. Okay. And then we have, like, we finally arrived. For any topological space, there's a set of quasi-pseudometrics Q on X, such that the generated topology is just A. Okay. And I do have.
Are you taking you're basically taking the union of all the topologies, right? But so the union of all the bases.
Essentially. Yeah. You have a subbase with a little bit of intersection. Right, to combine together two bases, but then essentially. Yeah. You combine together all of the bases and then form a subbasis. Yes. Right. And here's a quick sketch of the proof. Right. So you take any open set in tau, and you define this Q metric to be 1 if x is in U and y is not in U, and 0 otherwise. And again, you can check, right, that it satisfies triangle. And then you take this set of metrics Q to be the set of all these Q's. And the idea is that this generates the entire space, because for any U, you can just take the ball of radius 1 at x using metrics QU, and that just generates U back. So it works. Okay.
Is this your
No, definitely. This is classical. I don't know who this goes back to. Yeah, none of these results here are mine. Okay. And now that we have this collection of these quasi-pseudometrics, we can now use it to define your topological properties. Yeah. And so again, we have like basically the same formula we've had a bunch of times. Xn converges to x if and only if Q of x and Xn goes to 0. But now it sets the hold for all Q. Okay. And you can define something as like sequential continuity is equivalent to for all Q, for all these pseudometrics in Q, you have Q of Xn and x going to 0. And when that happens, for all m in the codomain, the distance between f of x and f of x goes to 0. Yes?
Is sequential continuity distinct from continuity?
Yes, it is distinct. And because we're not working over first countable spaces, we're working over very large spaces. So the sequences don't do a good job of characterizing topological properties at all. And a nice example is you can just take a topological space where every convergence sequence has to be constant. Yeah. And then sequential continuity is trivial, but continuity may not be. And then you also have your non-topological notions that you can now use. You can find Cauchy in the same sense. Q of xn and xn goes to 0. But now this has to hold for every one of your pseudometrics in Q. And then you can define this sequentially uniformly continuous. And again, this differs from uniformly continuous. Yeah?
If we did this definition of building this big set Q on a space that is metrizable already,
Yeah.
will sequential continuity without new Q version be the same as the regular?
Yes. Well, it's because you have agreements for like all your topological properties. Your sequential continuity and your convergence is the same. The only thing that will differ is what like a Cauchy sequence is and what the sequentially uniformly continuous maps are. Right? They'll differ because they're very much sort of these metric notions. So the sequentially uniformly continuous, right? It's very just similar to your definition of sequentially continuous. Right? But rather than xn and x, you have xn and y. Michael?
Do you think compact rate just corresponds to continuity in these spaces? With this metric, the one you constructed?
Oh, the one I've constructed?
Yeah.
Yeah, I don't know.
It should, right? Because
I don't think so. But maybe.
yeah.
Yeah, but in general, we're just taking a collection queue, so you can pick a collection queue where they don't coincide. Yeah. Okay. And then there is a definition of continuity, but we're going to have to work out epsilon delta. And it's not the nicest of definitions, but it's one you can use, right? And very much uses these quasi-pseudometrics. So you have continuity if and only if, and for every x, so you continue with every x. And for every metric, quasi-pseudometric in the codomain, and every epsilon bigger than 0. So starting off the same way continuity does, but also taking a particular metric, quasi-pseudometric in the codomain. And then we're saying that there exists this countably many collection of quasi-pseudometrics on the domain, and then there exists delta bigger than 0, such that your regular continuity holds. Right? You're less than delta in the codomain implies you're less than epsilon in the codomain. Right. And then you can do the same thing for uniform continuity, except now you just can't have everything dependent upon x. Yes?
Why does finiteness work? Why?
We'll see that in the next slide. But yeah, finiteness is really required for these things. If you require it just like always, it's far, far too strong. Yeah. That's why I like the sequential definition. Much nicer. Alright. So we had the theorem that every topological space is generated by these quasi-pseudometrics. If your space is nice enough, we really need the quasi part, and the answer is no. If your space is T3.5, so between the point and the closed set, there's a function which is 0 on the point and 1 on the closed set. And you're actually generated by a collection of pseudometrics. Right. And then if your space is also Hausdorff, then these pseudometrics can be chosen to separate points. So for distinct points, there is the pseudometric such that the distance between x and y is bigger than 3. So this, right, it doesn't guarantee that you can be generated by a collection of metrics. It's not saying for every q, the distance between these 2 points is bigger than 0, only for one of them. So generating a collection of metrics which generates your space doesn't have the nice conditions for it that I could find. And we sort of saw in the RTR example, right? Very nice space, and the canonical thing you do only generated as pseudometrics, right? This dx thing. Right. Cool. All right. So now we've made some progress, right? We moved away. We went from metric to pseudometric to quasi-pseudometrics. Now a collection of quasi-pseudometrics. Right? But there's a sort of way to get one object back rather than having to deal with a collection of possibly uncounted many metrics. And so that we can sort of return back to your definition of quasi-pseudometric. And there's one thing in this, we sort of never change your definition of metric. And it's this codomain here. We always said that the distance between 2 points has to be this positive real number. And you can change that. Yeah. You can just go to any space V which is nice enough. And if you want to know what nice enough means, you can read the paper and then the one that's off screen. Okay. So look, for what do you actually need to have this definition make sense? Right? You need to have some notion of 0, some notion of less than or equal to, and some notion of addition. Right? And these things sort of have to be nice enough. And so we can just combine together all these quasi-pseudometrics we generated into one big object. So we're going to start off with the quasi-pseudometrics we had before, and then we can combine them all together into one object that maps into 0 infinity to the I, so the I indexing your quasi-pseudometrics. And all we do is just to define that the distance in the ith component is just the distance in your ith quasi-pseudometric. Like that. And then if you define like this less than or equal to and these additions coordinate-wise, then you satisfy these two things. Yeah, just because each qi is a quasi-pseudo-metric. Now to generate the topologies from these things, it's not necessarily the nicest of things. You can tell because immediately we've got a pi I appearing. Yeah. So it's your regular ball definition, but we only require that in the ith component of the codomain, you be less than epsilon. And then all these ones, they form a subbase for the topology. And then we have that every topological space admits a continuity function that generates the topology.
This is just rewriting the theorem.
As currently, it is just rewriting that theorem, but the neat part about this, and it's the part that I don't fully understand yet, is that you can switch up this codomain. So I've written it here for 0 infinity to the I. You can take it to that set Z with the nice ordering and nice addition on it. And I don't know much about it, but from what I've read, it's just like when you change that, you can get out. It's like for some problems, this 0 infinity to the I is not like the best choice, and it's more like canonical codomains that you can pick. Yeah. Same question.
Related apologies if it's a bad question in light of this. But so this up here, these balls depending on index I depends on this construction as being in this
Yes.
0 infinity to the I. Do you know if we can get a topology out of a general continuity function with whatever nice enough codomain?
Yeah, so for the nice enough codomain, right, it's a part of left there, you have a less than equal, you have to have a plus, and you also have to have a dignified subset of positives.
Right.
Yeah, so you have like dignified subsets which you use to generate balls. And so here the dignified subset is sort of just like only like finitely times, like it's non-zero, and the rest of them is just equal to infinity.
Right.
It's the same thing. Yeah.
Okay.
Do you only need 1 0 or can you have multiple?
I've only seen it with 1 0. I'm not sure if you can also have multiple zeros.
Like if V is some lattice, for example.
Yeah, the lattice the stuff I've seen requires 0 to be a continuum.
Does the topology still satisfy that lattice condition in basic topology?
What do you mean it satisfies that lattice condition?
Can V just be picked to be the topology, and then
Can V just be picked with the topology?
to be the topology, and then if X is in open set, make the distance V.
Exercise to the reader. Yeah, that's not the canonical construction that they use. Yeah, because then you have like the whole product space, and then you have the triangle inequality to try and satisfy. So I'm not so sure if you run into problems there. I would assume if it's not the canonical construction, it's probably runs into problems.
Right. That's a good point.
Yeah, I don't know. Alright. Okay, stuff doesn't like being on screen. Alright. So we have introduced this pi I, just look at the ith components. And it's not equivalent to just use like a standard ball construction. I'll just take epsilon in this sort of set of positives. Right? All the things in V, sorry, you have to use a set of positives. And the reason, if you think back to like our original construction, what are we doing in this? We require like each component to be less than like epsilon I. So in terms of balls, you're intersecting over uncounted many of them. And to form these sort of sub-basis constructions in the previous things, right, that requires only finite intersections. Right? So doing an uncountable intersection, you don't generate what you want. And that's why finiteness has a tendency to appear. All right. Question?
So would that be the equivalence if we allowed D to take on infinity as a value?
Yes.
Okay.
Yes, in the definition of even a metric, you can allow it to take on infinity as a value. And it's equivalent. Yeah. Any topology that you generate with a metric taking to infinity is just a metric topology. And the way you see this, you take this like you could call it extended metric, it takes away infinity. You consider, pull out D, is it D tilde, which is the minimum of D in 1. And that will generate the same topology. Now that you've taken the minimum, it's now a metric. Good. So now, that we have these, you now have nice notion that you put the product topology on the codomain, like everything from metrics sort of comes back. A sequence converges to X if and only if the distance between it goes to 0. Okay, there's no need from the previous construction to index over all metrics. You just go to 0. Okay. You're sequentially continuous if d of x and xn goes to 0, then e of f of x and f of xn goes to 0. The same construction as always. Cauchy is Cauchy, and sequentially uniformly continuous is exactly as it always is, which is quite nice. You run into problems as soon as you want to do like epsilon delta, and it's still runs the not pretty far. Now it's long, and now it's not just like what you see in metric spaces. So it's again basically the same construction for every x and for every j in the codomain. There's this finite subset in the domain, and this delta such distance in the domain less than delta plus distance in the codomain less than epsilon. And then if you want uniform continuity, it's the same construction as always, except now none of your things are allowed to depend on x. Okay, and that's the last slide. Thank you.
So the reason we want to do this is because we want to recover these notions of Cauchiness and things you get from metrics.
That's like the idea is to sort of like use like the properties of the metric to do things, and Cauchiness is one of the things.
It's a bit, yeah, right. So, but of course, when you do this, like you're kind of the whole notion is so very different. Is it like useful at all?
Yeah.
To do this because you get.
Is it what?
Because I mean, with the metric, you get nice notions of distance with neighborhoods and that. But even Cauchiness here is going to be very funky compared to have you seen good cases where this has been helpful to prove a theorem?
I have not, but
Yeah.
this is something I need to start looking into recently. The more I read up on this, I'm like, wow, this can actually fix so many of my problems.
Okay.
Yeah, yeah, it makes everything so nice because this is like a lot of the stuff on metrizable spaces. That like one of my favorite proofs is just like extend to the completion, which requires Cauchiness.
Sure.
Make all your functions uniformly continuous and extend those, and then solve on the completion. And so it's a purely topological like statement, and the proof is very non-topological, requiring these completions and this uniform continuity, and all these things.
So.
So why are you looking at this stuff?
Because it's just like because a lot of things I don't know how to extend to topological spaces.
Okay, but what's the area you're studying?
The area it's in convergence and measures, in the weak convergence and measures. Yeah, and so much of that theory is just on metric spaces, and a lot of the extensions to like topological spaces is to something like sub-metrizability. So like it's essentially just metric. And so like I think that there might be some stuff here when you use these sort of constructions where it makes it much easier to port over these like proofs from the metric case to like the topological case.
So there's, as you know, there's other notion of deformity.
Yeah.
Called the uniformity.
Yes,
And
that's
topology, right?
Yeah.
What is the advantage of this method over just the simple? I think it's simpler uniformities. What is the advantage of this method over that?
Well, it's just because you can start thinking about it in terms of distances. It's just like you no longer have to think about this in terms of open sets.
So indexing.
And also, I think you should gain more than just uniformity itself. I don't know, but I feel like something like Lipschitz continuity should admit an extension to the sort of much more generalized, like a collection of pseudometrics or a different codomain. I think it should just like immediately by definition. But I would highly doubt that can be defined entirely by the uniformity itself. Yeah, because like you can have two like different metrics that generate the same uniformity.
So is the only difference here that you have an indexing of uniformity? You have a notion of how big an epsilon ball is.
Well, it's sort of just like what, because like even like a metric, you can sort of consider just like a selection of dignified subsets. You selected out like the balls. So actually you can do the same thing inside like the uniformity where you select out these like nice notions in the diagonal.
Right.
In the product space, so not the diagonal.
But it's still though, this goes more further because uniformity, every subspace is uniformity.
Yeah, but it is generated by quasi-uniformity. And that's where you get, because if we jump back over to wherever it was, this one, the family of pseudometrics. Yeah. So a space is T3.5 if and only if it's generated by uniformity. And that's set, and the uniformity is always generated by a collection of pseudometrics. Where you go to the quasi part is you go to the quasi uniformity. Christian, do you have a question?
Yes. You talked about like 3 seconds left and right Cauchy sequences.
Yeah, 3 seconds, yeah.
Are they ever equivalent? I mean, sorry, obviously. But in like, are there any other requirements to make them equivalent? Something special about that Cauchy being right Cauchy?
No, the reason I said it for 3 seconds is because I know about 3 seconds left. About the left and right Cauchy sequences. Yeah, I mean, I can probably give you the definition might make a little bit, because normally, right, it's like just like for n and m like bigger than or equal to n, the distance between x and n. Alright, they're big enough, is that readable?
Yep.
Readable. Yeah, so if you go like left and right, I think when you just do this, right, now it's like a left Cauchy sequence, you require n to be bigger than m, and you want to do the other way, make m bigger than or equal to n.
If the set of metrics over a nice space, rubbish like, is like topologically uninteresting, they're all contractible, Riemann metrics, whatever, but they are geometrically like very interesting because you can put functionals and like minima of whatever energies, and you can flow to good metrics. But is there any function on this space of pseudometrics or?
No idea. Yeah, I have no idea how nice of a space the collection of these things are.
And if I gave you 2 pseudometrics, let's say, just to play it easy, would there be any way for you to assign an invariant to those that tell you whenever they are using the same topology without running the whole machinery?
And they say when they generate the same topology.
Or to say when they don't, for example.
Well, it should be like the...
Without actually...
Yeah, the only way I know is like usually the definition like there's a ball here, it's intended the ball, another one, and then there's a ball inside of that, the other metric. Yeah, that's the only notion that I know, even from the metric case. And that will extend over to the pseudometric case. But I don't know like anything more interesting beside that.
Is there, I know the answer is no, I'm not that you're ready, because no, something about maybe the quantity type of the nerve of this.
I don't know, sorry. Be excited, Michael. If Michael will solve it for you. Yeah, there you go.
Did you say you were like studying the completions of these topological spaces?
Well, it's just that by the completion made in appearance in the proof. Yeah, because in like the measures on non-complete spaces can make really garbage.
Right.
But measures on complete spaces are much nicer. And so the measure 3 problem users will just like move to the completion and sort of extend out the measure. Now it's much nicer. And now you can work with it.
And have you had success, like, sorry, are you saying you've had success doing
that in the metric case?
In the metric, okay.
Yes. I think it should automatically extend to like the pseudometric case.
Okay.
As to whether like how far it extends, I have not tried.
Interesting.
Yeah. Yeah, and something else we've been thinking about is like the Wasserstein space. You know what that is? Nah, well, it's something to find a metric space. It's roughly like you integrate dx, like t of x, over d mu of x, and then you try and find like the name of this for some nice thing. Right? And sort of these sort of notions, right? It's very much a metric space thing. How do you generalize this to a topological space? Just like
she did that.
You did that?
I have 2 papers on similar stuff.
Ah, that's nice. Yeah, because I've been seeing this.
I didn't generalize, I mean.
Yeah. Because like it's like because now, right, you can just replace this now with one of these. And I wonder just like how easy everything extends.
Great, so I suppose
Yeah.
So this obviously related to some local statistics, right?
Yeah.
Could you explain?
Explain what the local statistics.
Yeah, like how this comes up with convergence of with convergence.
Yeah. Do you know continuous convergence? I think it's really because it's just like it's like fn of xn, right? Like it goes f of x. Oops.
It is fn of
fn of xn. Cool.
fx.
So you have like, make that longer just like, because you have, right, like fn f, like defined on x, say to the reals, make it nice. And then if xn converges to x, means fn of x converges to f of x.
Yeah.
Yeah. And then there's this nice result that in the weak convergence, yeah, measures was converged like weakly here. Right?
Yeah.
Then you pass it through like the image measure, and that also converges weakly.
Okay.
Yeah. And there's something really sort of strange about this, is that continuous convergence is equivalent to uniform convergence on compact sets with a continuous limit. So essentially uniform convergence on compact sets. Yet this theorem holds on when each of these probability measures assigns probability 0 to every compact set. And so it's sort of like it's this strange idea about why this is actually hold. And then when you can sort of this extension to the completion type thing, now all measures on a complete like simple metric space are tight. So there's complex sets of arbitrarily large probability. And then you can use like uniform convergence over those to get you nice things. And so what I was working on like extensions of this principle. And like the standard proof of this, I could not figure out a way to go. So if you have like this uniform on compact sets and the complex sets of large probability, then you can go places. So the idea is you extend to the completion, solve on completion, restrict back.
So what kind of spaces are the probability measures of?
Well, this takes part of the abstract theory, so this over like metric spaces. And in practice, you have like weird spaces, like reals you can do with that assumption. You do like these like infinite dimensional like boundary space type things, L infinity type stuff. And that's where stuff starts to get more interesting.
Yeah.
Although L infinity is complete. But
The compact sets become more.
yeah, compact sets are thin, right? And conventional
Yeah,
spaces.
yeah. Because of course we understand we can convergence over R quite well.
Yeah.
But when you move into infinite dimensional space, it becomes harder.
Yeah, because all the stuff become like much more subtle.
Yeah.
And then you have like the complete case.
Yeah.
And the separable case, you just like to do things in that, you start like going into like independence instead of C, which is interesting. Yeah. Which is crazy. Yeah, have I shown that before?
No.
I really showed that at some point.
Sorry.
Yeah, but that way we have independence that actually shows up in this analysis. Yeah.
You guys let us see.
Yeah, ZFC, yeah.
Any other questions?
Yeah.